So I want to start a list of reasons that this is a useful estimate, a desirable estimate of the slope of the regression line. There are other slopes that might be better, right? If I draw a bunch of data points and we each just take a marker and try to draw a line through them, we might get different lines, we would get different lines, and we could each argue about why we like our own line better. So I'm going to give you some reasons that this is the convention. Why is this one special? And I'm going to list those reasons over here. And the first reason is the one we've already said. We've minimized the sum of the squared residuals. Okay, that's something desirable to do. So the way we even got this expression was by minimizing the sum of the squared residuals. Why is that a quantity we like? Well, it's related to variance, which is a conventional quantity, a conventional way to measure variation. So this idea of minimizing the sum of squared residuals, the same as minimizing the variance of these points from the line, and that fits in nicely in terms of conventional ways to do statistics. What else? What else is desirable about this quantity? It turns out that these are unbiased estimates. So the slope estimate and the intercept estimate are both unbiased estimates. Let's talk about what that means. So far, I've been talking about just one data set. You have a data set and you're trying to fit the line. But if the model is true, in other words, if this line is how the data is being generated, this line really does represent how the mean of y corresponds to x, then I can imagine that this data set I have is only one of many data sets that I could have had, right? If the way the data is generated is for each x, the mean of y comes from the line, and then we add a little bit of normal error to find a data point, well then this is drawn here as one data set that I could have. But it also could be that when x is equal to 10, here's the mean, and I randomly draw this value next time, and I have these other data points. Or I could erase that again and draw slightly different data points, all coming from this model that the mean of y is related to x on this line, and then I just have some random error away from the line. And the fact that there's this random variation away from the line is what tells us that every time we drew a sample from this model, we'd get slightly different data set. Again, if you sat down to do a simulation in R, every time you drew values of y, given the model that this line represents the relationship between the mean of y and x, you'd get a slightly different data set. And so you could repeatedly draw data sets, fit the line, and calculate these two quantities. Okay. Again, you could repeatedly draw a sample of y's given that x is equal to 10 and the mean is here. You could repeatedly draw a sample of y's given that x is equal to 20 and the mean is here. You could repeatedly draw a sample of y's such that x is equal to 30 and the mean is here. Each time you draw those samples, you have a data set. You can plug in the values, get an estimate of beta 1, an estimate of beta 0, and write those down. And then you could throw away your data set, draw another data set, draw another sample here, a sample here, a sample here, calculate those two quantities, write down your estimates of beta 0 and beta 1. And if you do that, you will get a distribution of estimates of beta 1 and a distribution of estimates of beta 0. And the middle of these two distributions, the average of all of your estimates of beta 1 and the average of all your estimates of beta 0 will turn out to be the true beta 1 and the true beta 0. This is a lot like what we talked about in terms of the central limit theorem. Even if you're just sampling from one distribution, even if we just have the heights of all women and we draw a sample of women, and based on our sample of women, we use the mean of their heights, right, to estimate the population mean. So we sample from the population of all women and write down the sample mean. Then we sample again from the population of all women, write down their sample mean. Do it again, write down their sample mean until we get a histogram of sample means. And one of the things the central limit theorem told us is that the middle of that distribution of sample means was equal to the true value. Another word for that is unbiased. The sample mean is an unbiased estimate of the population mean because on average, if I repeatedly drew samples, the sample mean would be equal to the population mean. That's what I'm saying about these two quantities. If I repeatedly sample from this model, and every time I sample, I estimate beta 1 and beta 0, and I make histograms of the estimates of beta 1 and of the estimates of beta 0, those distributions of my estimates would be centered on the true quantities, and that means they're unbiased. Not only are these expressions minimizing the sum of the squared residuals, but on average, they lead to the right answer, which is a good thing.